Well, maybe you back once, but this one is extremely noisy, so I cannot hear you. Okay, most welcome. Thank you very much for making it able that we only today meet for the first time. So I know you like presents, you are here, that's good, and we'll keep it this way. What I would like to be doing today, we had a second video, which I hope some of you had a chance to look at. What I would like to do is maybe give a little bit of a wrap-up from what we learned there and helping you to understand some very fundamental things. And maybe if I collect, what is limiting this? Maybe start very simply. When we are talking about communication, what is the thing you talk about most when you use this? Pardon? Battery life. Battery life, that's very good. Yeah, that's related to what we are going to discuss today. And actually, battery life is a very smart answer. It's very timely, and we all still learned at the moment that we can save a lot more energy than we originally thought doing the same thing. So that's exactly what that lecture is about. We can do radio communication, and many people have thought about this because your battery life is weak. Yeah, so you only have so much. And in a way, this is a good model for our planet because we only have so and so much energy. And in a way, you learn a lot on the system level how to do that. Yeah? Coming a little bit to the problem we are facing, have you thought about that? So this is the growth of the data rate. Maybe to get your impression, what is the reason for, what is the reason for us consuming an exponential amount of data? Why is that? Have you thought about it? So this is what's proposed. So we are using exponentially globally, but also in Germany and other countries, we are exponentially rising our data rate, or the amount of data we are consuming or using. Why is that?
Maybe it's Moore's law.
Oh, that's already very good, yeah, very good, but does everybody know what that is? Moore's law is essentially the idea from semiconductors that with every so and so much time, typically 18 months, we can put the double number of transistors on a wafer. So that's, in a nutshell, that's a technical development. But there's more to that. Why do we use so much data?
There's more cloud applications and also more users of internet worldwide.
Yeah. So there's definitely more users, but does somebody know how many cell phones we have on this planet? So far produced? It's about 20 billion. How many people are we? Unfortunately, it's already 8. So fortunately, depending how you see it. But so you see there's already a mismatch. So there's more cell phones than people, so which is a bit crazy. But there's another reason why this is growing so much, which we think why it's still going on exponentially, because you could say everybody can only look at one phone. What is driving this also? You said cloud, yes. What is communicating in the cloud?
The users with servers worldwide. So.
Yeah, it's not, yeah, but there's something very subtle that you are avoiding to say. It's not only us communicating, but it is servers, or more generally, quite simple, it's machines. It's M2M, what we call that. So this is growing heavily. So even if all of us hold a phone, and that's, we all have in the so-called developed countries, we have more than one phone or more than one machine. I'm already just using 2. You see how it works. But of course, not everyone on this planet is in the same situation, but it's essentially the growth of machine communication. Yeah, so we have servers in indirect ways. It is production machines. It's very stupid things like a ticket counter at down there. It can be anything, and that's growing. Yeah? And we are digitizing strongly. Yeah? Or you could say this is not a problem. But somebody already started. You started with the energy problem, which is smart because energy is definitely limiting us. Yeah? But what is limiting us on the channel side? And that is something which this lecture is very much about frequency and data rate. Yeah? So we have frequencies, we have optical frequencies, we have audio frequencies, I'm talking to you, we have microwave frequencies, and the other idea is there's data rate, so there's bits moving. But what is the relation between the two? Yeah? And the first answer, and that is something I already put out in a way, is to get a very principal understanding is that if you are in any spectrum, any frequency that you can use, there's an associated channel capacity. Yeah, so if you have a frequency which transpires waves or any kind of carrier information, as we say, then there's a fundamental relation between what you can transport and what you can essentially what you have. Yeah? So there's an idea that if the spectrum starts from 0 hertz to, let's say, a terahertz, which is 10 to the 12 hertz, and you have that, you can take chunks out of that. Yeah? And this is this number which we have here, which is the bandwidth. Yeah? So for example, just to get an example for all of us, what is the frequency of this roundabout? So this thing is we're using which frequencies?
Which one?
Some of them, any. There's many. First of all, there's many, very good, yeah, but it's still relatively limited.
I think 2 to 5 gigahertz.
Gigahertz, so that's very important. And one of this, when you're in a system, yeah, so you could say, why talking about cell phones? That's boring. Yeah, but of course, they're interesting. They have a lot of capabilities, but there's something you can learn. And the point is, you have gigahertz as communication carrier. Yeah? And we could have the same discussion, for example, also for light waves. Where do you use light waves? In the optical fibers, and if we didn't have those optical fibers, at least the transmission into the internet would not work well. Yeah? So that's very important, because optical communication is the backbone of the internet. Yeah? And no matter what we take there, we have an absolute number. So the C is what you want. So C is capacity. You want to download a video. You want to transport an amount of data. You want to know how your latest health investigation or examination was done, and you want to download the data. There's a lot of it. So that is what is growing. And then there's the associated bandwidth. Yeah? And this bandwidth idea is an absolute number. Yeah? So for example, you get within a gigahertz, the maximum bandwidth you can accommodate, that's what we have to learn, is roughly around the gigahertz. And we have to understand why. So there's chunks out of the spectrum which you can take out and use. Yeah? So this is directly proportional. Yeah? And for example, the answer we already learned in the first lecture, why do we go for optics? Because obviously the frequency of optics is higher than microwaves. Yeah? And that is, so you have then something like 30 terahertz, a lot higher than what we use for microwaves. Yeah? And what is, of course, the obvious advantage of these? So it's inferior. Yeah? So this thing does not have the capacity as optics. But why do we like it? What is the point about this? Why do we use this? Yeah, so it's not connected. Yeah? And this is a very strong argument. Yeah? So you can take it anywhere. Yeah? And the fiber is very powerful. But one idea you have to understand in a system is not just what the system is, but what you have to do it is. And what is the most expensive part of a fiber system? It's very trivial. To get a fiber, what do you have to do to get it somewhere? Hmm?
You have to put it in the ground.
Yeah. That's the racket. So you start digging into the ground, which is the most expensive part of it. Yeah, so, and you can see that in Germany we are very slow and very reluctant to do that. This digging into the ground has a lot of implications, and a lot of fiber was done when we had reunification, which by now is 30 years ago, and we have always trouble in putting out new fiber. Other countries are more smart than we, but just to think about that. So there's, independent from what the actual system is, there's implications, yeah? And the nice thing about the cell phone is it has a capacity, and I can use something else, and I can directly build up essentially ad hoc a network. Yeah, so that's a big advantage. Now, and the point now is, for any of these capacities, there's this limit. Yeah? And it's a very fundamental theorem, so I cannot really prove it, so it's just there. And one thing you have to understand is, normally when we are miscommunicating, we are starting to get louder. I'm speaking louder to get more information to you. Of course, in teaching, that's probably the worst thing you can do. However, you're also being told by nature that it's not a very efficient process, because if I'm getting louder, my effect on the capacity is only by a log. Yeah, so I'm getting louder, and yes, I can increase my capacity, but only so and so much. And of course, before we start about the N, the P is the power. And can you give me the indirect arguments why, essentially there are two, why we cannot infinitely increase power? So why can I not, at any type of transmission, why I cannot simply increase the power? I think one was already given, but maybe you repeat that. Why can't we radiate thousands of watts of microwave into the air?
First, too much energy consumption, and maybe harmful radiation.
Yeah, okay, so that's very good. The two answers, very nice. So the first thing is, again, this limit. So it's not only true for the cell phone. In a system, whatever it takes, you only have so and so much energy. Yeah? And what is particularly bad, that's also something why I'm standing here, is the conversion rate. Yeah? So I assume I have power with information. But already to get there, yeah, we have to spend a lot of energy, electrical power. Yeah? And the first thing you have to understand, who is sensitive? And then you start thinking, yeah, energy, power, electrical power used to be cheap. Now we are learning it's never cheap, and it was never cheap, by the way. But the idea that if you have a certain amount of power, to get it to the point where you transmit, it has already cost a factor of multiples to make it. Yeah? And the other thing is, you said radiation damage or something like that. Where can you see that? That microwaves are critical to fiber or to any type of tissue?
In the microwave.
Yeah. So you can make that experiment, put something into the microwave oven and turn it on and go way too far. And there's not much difference between the chicken or whatever is comparable to my hand, at least from the absorption properties. Yeah? So that's, there you see, this is obviously damaging, you can see that, but already before that, long before that, we tend to think about that. So, as I said in the first lecture, there's a limit. Every band, and it's not logic, it's not necessarily that at 27 gigahertz you can, it's 27 megahertz you can only put a watt, and then maybe the adjacent band is only 2 watts. Sometimes it's, for one band we have 1 watt maximum power allowed, and in the next band you can do radio transmission. Yeah? So for example, for a broadcast you need several hundreds of kilowatts to do that. Yeah? So power is inherently limited, not only if you are thinking about energy as a resource, but there's a limit. And then we come to the point of what is given then as noise, and that was the famous idea of Shannon, to say there's noise which limits. That's a fundamental limitation. So the idea is, whatever you do, you always have noise in the transmission. The question is why? How can you substantiate that for yourself? Why is there noise in this room? For very simple reasons.
Because there are other senders. So if you have two stations, one can send something and the second one detects it. And also we have a lot of senders that are not intended to send. So we have the cars outside sending noise in here, even though they are not intended to make sound.
Yeah, very good answer. I'm afraid we wouldn't, what you said, mostly is not called noise, because noise is much more fundamental. What you would call is other sources, we would call that effect more interference. So even in an ideal world, if we had nothing in the universe except from you sending, this would be true. So this is a fundamental law. Yeah? And noise, what is the most relevant, how can I understand very easily or that noise is there, or what can you do to diminish noise? There's only one way of really doing that nicely.
Lock-in amplification. Lock-in amplification.
Yeah, that's already a technical trick, but much more fundamental. What is causing noise in this room? Very good. That's a fundamental thing. So the essential idea that at very low temperature, at zero temperature, which is minus 273.184, there we would have no noise. And only because, but fortunately we are living, because our cells essentially need a certain kind of temperature, we are living at 300 K. So that means, and this noise floor, this power which is everywhere, fundamentally is proportional to the temperature. Very good. Yeah. And the only way you can reduce noise, apart from the technical tricks, they are also nice, don't get it wrong, but there's a fundamental way. For example, the radio astronomers do that, because if you want to listen to very weak signals which come from far away, whatever where the universe was born, you cool down the receiver to 4 Kelvin. They all have these fridges in the receivers, and this is another way. If you think of a fridge inside the cell phone, this is not really making sense, because we cannot cool parts of this thing down to 4 Kelvin to reduce it. Yeah? And that simply puts us into a position that essentially you cannot increase the power. We think a lot about noise, and I like your idea about the lock-in and the noise discrimination which we are trying, and we are doing a lot of engineering to keep the noise down. So not to add noise, that's the better idea, yeah? Because you said everything which we send through a system, for example, all this stuff which finally will come out as noise, will finally end up in the system as some added noise floor. You're right to say so, yeah? But there what we are trying to reduce is not adding noise when we amplify, for example. Yeah? And now we went through all these considerations, and what is the only fundamental way we can really help ourselves in getting more capacity? W, the bandwidth. And that's very important. And one idea which I like very much about the idea about the interference, there's another idea. If a spectrum is taken, so we take a couple of megahertz, around 2 gigahertz, for example, then for very fundamental reasons it cannot be used by somebody else. So if we use that spectrum, it's taken. So if it's run, yeah, and just to say it very clearly, this is the fundamental maximum. Yeah? And the rest of the lecture will essentially be devoted to tell you what we are doing to get close to that maximum. Yeah? Because one thing we also technically can say today, when we're using these things, in most of the frequency bands, we are living close to the maximum. So we are designing systems which are really taking every hertz we can get from the spectrum as capacity, yeah, because we are so much driven by that exponential curve. Yeah, so that's the idea. And here it is just the simple idea when you speak about amplitude noise, this fundamental idea that noise is simply there. So when we are going back to this input-output relation, which we will use a lot, there's simply, when we are reducing the input power to a system, there's a learning that at some point, at some power, even if you reduce the input power, you will still have a certain fraction of noise covering. So there's a limit where you cannot get below. Yeah? What is also very surprising is when you think about these systems here, these cell phones are actually getting quite close to these noise floors. Yeah? So the power which we still can detect if you're running a rod and just losing connection is about 10 orders of magnitude lower than what this thing, or 13 orders of magnitude lower than what this thing can maximum put out. One last question before we go into the details. Why do we need so much power at all to transmit? Which physical thing which is around us makes this happen? It's also a system idea. So why do I need a kilowatt of power for a radio broadcast station? What is causing the idea? Something we cannot change at all. So why, for example, if you still listen to old-fashioned SWR3 radio, why do they use 100 kilowatts of power to supply Baden-Württemberg or parts of Baden-Württemberg? What is the root cause? Why they're putting up 100 kilowatts? You can look into the out of the window. It's exactly correct. What do you see there?
The atmosphere.
Okay, thank you. And what is this atmosphere?
Medium. And medium of transmission. It could be medium of transmission.
It's a medium of transmission, and ideally, if it's a blue sky, what do we see then? What is that? Is it ideal? Is it more ideal when we see that, or what do we have then? So if we have normal air in comparison to the ideal situation, what is normal air? Is this good or bad in terms of transmission?
I think it's good. We have clouds and we have more absorption. More water.
Yeah, very good. Water is a point. But there's a systems idea behind that. Because we are not designing this for this weather. Although it's nice to be in the sun with this, but we are not designing it for this. We are designing this system for the ultimate thunderstorm. Yeah, so if you're standing there completely showered down by rain, very bad weather, night, whatever, this is what this system is designed for. So ideally, of course, it should also work when the weather is nice, but the complication comes because the fundamental absorption of water in the atmosphere is shutting the system down. Yeah? And some of you may have observed that when you for example, have a satellite transmission again on TV, and if it's raining heavily, suddenly the transmission stops. It's not like internet, which is always there, hopefully, but it's reduced. So the idea here on this thing is we are designing for the worst case in a system, not for the optimum. If it was always like that, that's the perfect day. We don't need much energy. We can take the power down. We save efficiency, we save power, yeah? But we also have to be able to put up the situation that it's very bad weather. And what I'm trying to say here, the whole story is defined by two things. It's about availability. And that's very important, yeah. And for example, if you ask yourself, what is availability? It's the same thing as having brakes in a car. So if you have a car, the brakes must always work. And for communication, we do the same. We say it must work. Yeah? It's a bit crazy, why do you need YouTube all the time? But when you come to emergency services, you're suddenly realizing, it better works. Yeah, so that's the system idea behind it. Yeah. Okay. And the signal to noise ratio, which is just rewriting the small equation, this is something we can always write. So the capacity is always the bandwidth plus signal to noise ratio. Yeah, so that's log bandwidth times log of signal to noise ratio. And that's the idea. So if you can improve or keep that up, the signal to noise ratio, it's of course good, but it has limits. And here you have a simple example where you see that the numbers matter. Yeah? And if you say now, for example, I spend a relatively high carrier frequency and I have a video bandwidth of 10 megahertz, which is not so shabby, and you see, but when I say 66 megabits per second, that used to be a lot. But if you, for example, look at Netflix or whatever, and you want to download, and you have 66 megabits per second, you're already starting, why isn't it 100? Why isn't it 200? So this number used to be high, and it's the limit. Yeah? But now you're saying, why not 1 gigabit? So there you're seeing there's really a limit which affects your life. Yeah? Okay. The next thing is, how do human beings do things? And for example, what is now bandwidth? So we only have that spectrum from 0 to 6 gigahertz, which we initially used for that. So that means the maximum we have is 6 gigahertz of bandwidth. And how do people start? Yeah? And the first learning you have in this lecture is that you can do things, for example, we tend to say every one of us gets a certain frequency or a certain bandwidth in the spectrum. Yeah? And then you're realizing, let's assume we have 60 people in this room. It's easier. 6 gigahertz, divide 6 gigahertz by 60. That means you have only 100 megahertz of bandwidth for each of us. So there's fundamentally a limit. Yeah? And you saw this is not really helping us. It's not getting us everything we want. And the next thing is that depending on how we do that, that is, for example, a frequency multiplex. That's what when you still had a very simple walkie-talkie. Yeah, everybody got a frequency or bandwidth to talk to. Yeah? At some point, you realize maybe this is not the smartest way of distributing that. Yeah? And that is now the next thing. So, for example, we use that concept that we are defining applications. So, for example, when you are now going to maybe mobile communication around 2 gigahertz, then we are assigning a certain spectrum to an application. Emergency stuff, communication, maybe frying a chicken, maybe whatever. Yeah? So this is the masking we are doing. Yeah? Now, in this signal, in this real signal, where's everybody? Who uses what? For example, if you assume this to be UMTS, where in this frequency spectrum between the two limits are you as individual user? Do you get a specific frequency, or how does it work? And what I can say is, originally in 2G, and if this was 2G, so this is what you learn as GPRS or GSM, sometimes it still shows here up on the top notch of our cell phones, then it would have been like that. Everybody gets a frequency. But you already know this without me telling you. What is the bandwidth you get in 2G? So GSM, what do you send with 2G? What type of data is typically sent still by GSM? SMS. How much data rate is that? kilobit. And there's a learning. Everybody gets a frequency. It's not so intelligent. Yeah? And to answer your question, this is UMTS, and we are all together in all frequencies. And then the question arises, if we are all in all frequencies, how do I make sure you don't get his data? So we mix. Somehow we mix in the spectrum, but apparently there's something which we have to grab which decides how effective I'm using the spectrum and how to get the transmission organized. Yeah? So that's the fundamental idea. And this regulation stuff is very boring, but the question is, what you can do then is, first of all, how to get the data on the carrier. Yeah, so because so far I only spoke about frequencies, but then we are coming to a point where we are learning, how does my information get on? Yeah? And there are two principles, and this is given here, for example, this is the receive path, assuming that you're listening to some radio. Yeah, so there's an incoming wave. And then I have essentially two concepts how I can get the information which is on the radio out. And this looks very complex. There's a mixer, there's a local oscillator, and then there's even some stuff behind that. But the way to look at it very fundamentally is always this. Yeah? Because people starting with the technology, they always do things in a simple way that everybody can understand them. Yeah? Because essentially, when you look at this principle, there's an incoming wave, somebody speaking, there's a mixer, and the only thing you need is some own frequency which gets close to what is incoming. So let's assume SWR, radio, so let's take 100 megahertz incoming wave, and then I'm tuning to this frequency, but not exactly. So I'm not tuning to 100 megahertz, I'm tuning to 99.99 something. This is my LO, and the difference is the intermediate frequency. And if it's so simple as we do it, then the information you've taken out is just the simple speech. Yeah, so you get, if it's very simple, the information content is just taken out. Yeah? So you down convert this information from the high carrier with a very simple diode, maybe directly to the loudspeaker, or maybe it has an amplifier in between. Very simple. Yeah? So it's just like how to build the first time the technology. And the only thing you really need is to have your own source for the detection. The other way of doing this is homodyne, and this is what this is using, and I will explain why in a minute. It's again a system idea. You track the incoming frequency. You exactly have a means to see there's an incoming frequency, 100 megahertz, and I'm tuning exactly on that frequency. Yeah? And then this local oscillator frequency I'm using is identical to what is incoming. Yeah? And the demodulator is then taking out from this process the data. Yeah? It's called zero IF reception because there's no intermediate frequency, and you could start asking yourself, what on earth, why do I need to know this? But there's complications which we need to account for. Yeah? And I would like to tell you how your self-learn works now in a way. The idea is always, how much do I have to have in my pocket to get a complex transmission done? So what can I put to the system that the extraction of this data is simple? Yeah? And why should it be simple? Because you don't want a full-scale oscilloscope to do the frequency tracking. You want something simple. Yeah? And one idea is that, assuming that your information is in this INQ, and we come to that, the question is, how do I put it on the carrier? So the carrier is just the wave which finally reaches you. Yeah? And the smart move is now that if somebody is intelligent and puts it on in the right way, then it's very easy for me to get it out again. And maybe detect also some problems. So for example, what could be a problem? That this signal, other than absorption, is somehow falsified. Yeah? And if I know, and this is the intrinsic knowledge which is built into the system, so if there's an agreement, which is the standard, that the signal is modulated on with a sine and a cosine function. So you take the wave and you modulate on with a known function, sine and cosine. Yeah? The trick is, if you know that, and of course you know what this is, what you have in your pocket. The people who built this also know what's happening in the base station. That's system engineering. So they know cannot be different. Yeah? So they know that there's an incoming frequency which is going to be minus sine and cosine of the frequency. And then you detect it twice. And the only thing you need in this homodyne reception is a small low-pass filter which takes out the original signal. Yeah, and the reason why you can do that is that you know the signal which is ideally incoming should be a sine and a cosine. If there's a deviation, you have already an information one. You can say there's a disturbance in the path, and that's intelligent. Yeah? And second, the amount of tracking you have to do, what is incoming, can be minimized. Yeah? So this demodulation scheme, which here, this is obviously simple. Yeah? So this is a simple measure because you just need a small diode, which is a mixer in the end, to take down the signal. The only complication you have in this thing is you need a local oscillator which generates some kind of frequency tunable. So that's the strong thing about this simple radio. And then if you compare this signal, you wouldn't understand why this is useful here in a homodyne concept. But we are answering a very important idea with this thing. For example, how can I understand that this homodyne makes a lot of sense? Have you ever asked yourself when you're walking around with this thing and there's never a disturbance? Yeah? And that's already crazy. For example, assume the base station is on top of that building and you're walking around the IMTEC this way and this way. And the problem is you get both signals to the radio. Yeah? So from this receiver idea, you can already detect where is the signal which I'm receiving less inhibited, where is it less falsified. Yeah? And this is what a mobile network essentially is about, to get the information to you without you considering where you are in the system. So you never ask yourself, do I go there to get radio transmission? You assume this is going to be there. It's again availability. Yeah? So if you ask yourself about the system, so essentially what is sent away is a modulated signal, which is essentially the baseband, which is the data. We will talk about why we are putting it this way. And the same way it's sent with another function, and maybe already an idea which helps you to understand the stuff. Mathematically, what is the relation of sine and cosine? If you just think back to your mathematical education, you had to learn a lot of things which you said, why do I need to know this? And it's no useful. Yeah. And you can say orthogonal mathematical crazy guys. This is very real. Why is that? Crazy ladies to be okay. Just to say that. The people in this, we can be on the same frequency, on the same frequency spectrum, if we are on orthogonal functions. This is what UMTS is doing. So every one of us gets a function which only you own. You have one, you have one, you have one. So we can mix the spectrum. And because you have the key, because you're told this is something which is transmitted in your individual communication, only you can extract with this function the signal, the information. Yeah? So that's the idea. So that's suddenly quite useful what you originally mathematically learned. So that's the fundamental idea. And now, what we have to do now is to get a little bit of feeling how we do things. Yeah, so there's always this idea we are gonna get to the Shannon limit. This is the maximum capacity we want to reach for a system. Yeah? And now we start doing things. Yeah? For example, in the frequency multiplex, you still have this idea in your head. Every one of us gets its own spectrum. Yeah? So you realize if you do that with a signal, the spectrum is, if we are trying to be independent, the spectrum is used up very fast. And we couldn't even guarantee a decent bandwidth for all of us using the whole spectrum which is available. So that is not very efficient. Yeah? So remember that idea, 6 gigahertz of bandwidth, 60 people, so every one of us gets 100 megahertz, and you saw that for 10 megahertz we got 66 megabits per second, and for 100 it's just 10 times. So the whole spectrum we have available is only 600 megabits per second for all of us individually. Yeah? So that's apparently not the smartest way of doing it. Yeah? So frequency multiplex is not smart. And you saw already with UMTS, they thought about it and improved to make better usage of the spectrum. So with this FDM, we are far away from the Shannon limit. But it was useful because when you were still a kid and you had this walkie-talkie, you were quite proud. So it was at least enough to talk to each other. Nobody interfered with you because you had your own quartzes and everything was fine, but it's not the smartest move you can do. So in the spectrum, there's something we like doing now, and that is something which we're now learning. Apparently this FDM, it's not the smartest move, so what do we do about it? And now comes a big moment in this lecture. If you say, I can do better, can get closer to the Shannon limit, I'm now lying to you in a bit, and you have to tell me where. So now I'm telling you, okay, we can shift the frequency together. So we can, instead of having these 5 McDonald's type of peaks, we are shifting them together, and obviously in the spectrum we are gaining spectrum. Yeah? And because we are in this way, we are moving closer to the Shannon limit. It is true, we can do that. So there's apparently a possibility that we can shift with this OFDM, and for those of you who have looked into communications, they've heard that. Yeah? Orthogonal frequency division multiplex, OFDM. That's what we all are using heavily in this thing here. And now we want spectrum. But it's a warning for you as an engineer. There's one sentence which will always be true in engineering. If somebody solves a fundamental problem, you have to ask him for the price. Yes? So now I'm telling you, okay, we can shift the capacity together and we can win spectrum, getting closer to the Shannon limit, winning capacity. Wow. Where did I tweak the but in my arguments? What problem am I causing? That's something which you should always remember. I'm making an assumption on the system. Yeah? So what I'm doing is, so far the spectrum was individual. Now I send this away. Will I receive this like that? In the atmosphere, it's not so problematic, but where do the problems come up? So when I'm sending something like that away, where does the problem come up? The problem is that if I'm making such a strong assumption, such a mathematical assumptions, I'm saying that this system is perfectly linear. in the sense that I'm sending one frequency and there will only be one frequency in the system. Is this true? That if I'm sending away one frequency, and especially when I send it through some gadgets like this, am I only generating one frequency? The answer is, of course, no. And there's the message. Somebody speaking a linear voice into a concert microphone, and if you tune up the volume, you know that at some point there will be trashing in the loudspeakers. Yeah? So the amplitude of the system is fundamentally limited, which means, and you can know that from acoustics, one clear voice shouted into a microphone, into an amplifier at its limits, gives some heavy banging in the loudspeakers if it goes wrong. Yeah? Some people like that, some people don't. I don't want to make a point. The point is it's changed. Yeah? So the trouble is, if I'm getting closer to the Shannon limit doing something like that, I assume that the system stays linear whatever it takes. Yeah? And this is one of the ideas which we will only perfectly understand in the end of the lecture. Why is this a problem to keep the system linear? The reason is, I think you said that, it's energy. Because it means no matter what I'm amplifying in this thing, I'm staying linear and I have to keep all the components linear, which means that typically my efficiency of doing so is getting very small. We have to learn why that is, but it's definitely not an efficient process. Yeah? So one fundamental learning for you is just to understand if there's a problem and somebody tells me I can solve that, you have to be careful what he or she is cheating into the argument. There's a fundamental limit, which we call bandwidth or capacity, and then somebody saying, I can solve that. You have to say, yeah, how do I pay for that? Keep it in mind. However, and here's now this is now what we are assuming that we are doing that. That is what we do in 3G. So this is here the time domain or frequency domain equivalently multiplexing. So this is the GSM, which you know SMS gives me only kilobit. And then CDMA, which is this code division multiple access, which is functions for all of us, 3G. Then we are all mixed. The trouble of this is, and this was the problem from the beginning, that the efficiency which you are designing into that is low. Why? Because you have to make sure that this signal, when going through the full system, is staying linear. So you solve one problem at the expense of a hidden parameter, in this case efficiency. And what is the problem about the efficiency? Mainly it's you again, or me. We want to charge in the morning, go do everything we want, come back at night, charge back in the morning. So there's a limit to the energy efficiency. Yeah? So we need, there's only so, and you can say in the cell phone it's very obvious, because in the cell phone it's very clear. It doesn't work if you don't have battery power, but we're using this in a lot of examples. So for example, the PCI bus, which we had in earlier computers, was also doing that. Yeah? Or this thing is also done, for example, in car locking. This technique is not only taken for communication. So, for example, when you tweak that key, this is exactly what you're doing with code division multiple access. Yeah? So it's a very generic example. Let's come to the idea of modulation. So apparently, my target is to put as many bits on this carrier as possible. And what can I do most easily? So which thing would I do in the beginning to do modulation? What is the easiest modulation which I can do here in this room? So how do I modulate my information just as I speak? amplitude, and a little bit of phase also. I'm speaking up, I'm speaking down, so it's typically amplitude, which I'm modulating. And what are we doing in this digital domain? Are we doing amplitude or phase modulation?
Maybe both at the same time?
Obviously both. It's not so clear why this is good, but it's both. And we will understand now a little bit why that is. So, and the idea is now you have a carrier which has some hertz. And now you want to put on bits. And this and what I'm telling you now, this is now just phase modulation. Yeah, so I'm putting on only a phase difference to signify a bit. And I just want to give you the example. So if I have this carrier and I'm modulating its phase, so if I'm just sending the carrier as it is, phase 0, so the angle is here, so this is the phase angle, yeah. So if I want to transport a 0 as a bit, I'm sending, somebody coming back, just a second. Okay. I'm sending a 0 phase. Now I'm changing the phase and I'm going to 180, so I'm sending a 1. So this is the kind of phase modulation, how we change how many bits we can put per hertz. So how many symbols have I represented with this? Oh, this is it's one digit, so to say. Yeah, it's a single bit. Yeah, and if it's 2 bits, then you are. If it's 2 bits, then I'm changing that principle already. But then it's not just it's binary. Then it's a 4 PSK. Then I have more states, and apparently, this is the first learning you have. The more of these black dots I have in this diagram, the more information I can transport. So in this case, for the certain carrier, I'm just changing the frequency in 2 states. So I'm transporting 1 bit. Now, if I did the same with 4 states, I can transport 2 bits. Because I need to make sure I can have all the situations assigned to that. So, and now apparently for the same carrier, I can put up 2 bits. So my data rate, effectively my channel capacity, are obviously increasing. But again, this trade-off, what is getting worse here? Why is this what I'm proposing also a bit of a problem? What would you say? What is making my life more, why is this more complex than this?
You have less distance between the dots. So if it's more noisy, then it's harder to distinguish it.
First of all, very good. But first get the argument for everyone. So the phase difference I have to detect between these 2 states is apparently 180 degrees, which is a lot. 180 degrees. So you say there's a difference, there's a full swing of the wave, and you say I either say it's this phase or essentially the antiphase, so which is very simple to discriminate. Yeah? And the trick is now I can of course take that further. Yeah? So and here it's, for example, for the 4 PSK, you see the different states, so there's always a phase difference of 90 degrees between the individual states I have to detect. Yeah? And if you look at this simple example already, you start to understand Shannon. Because what did Shannon say? It is the channel capacity in an information system in the presence of you said it, noise. That's the famous paper from 1944 where he described this for the first time. In the presence of noise. So normally you know amplitude noise, so there's a certain limit in power, but here it's even same thing, similar idea. You say there's a bit uncertainty about the phase, I can still discriminate. Yeah? And here what I have to discriminate is 45 versus 135 or versus 315, which are the neighborings. Yeah? So I always have 90 degrees to make a distinction between the bits. So this is easy. Yeah? However, now if I increase the bit rate to get closer to the Shannon limit, I would now take not 4 PSK but 16 PSK or 32 PSK, and then the phase modulation, which is just assigning the number of bits I can put on that carrier, is constantly reducing. Yeah? To the point that I'm not able to discriminate between the states. And that for a communication engineer is always the nightmare, because a communication system is only useful if you can re-extract the data. That is very important. So the system is only valid if you get your data back. Otherwise it's useless. Yeah? So we always have to define a point where we say, wait a minute. Now it's not working anymore. Because if you start losing bits, that's not what we want. Yeah? So we can increase, but there's a limit. And now, that's not only phase, you were correct, because it's not very, doesn't require too much fantasy to say, okay, he or she is modulating the phase, why not also discriminate the amplitude? And of course you're perfectly right to do so. And then you do something like QAM, you have quadrature amplitude modulation. And then, for example, this is a specific case where you have a given phase of 90 degrees. That's one way of looking at it. And then you are doing exactly this thing what we were describing with the cell phone, that you're sending away two signals which are orthogonal within the own carrier already. That's what we call then QAM. Yeah? And more generally, and that's just to give you a flavor of why things are complex, we just had these diagrams. So the 4 states. If you're now going through the system and do a real communication, you're ending up with something like that. And that gives you, for the first time, the idea, because this is essentially, when I'm now using this is exactly what I'm doing, because I'm jumping between the states all the time. Because I constantly, over time, change the state of those bits. Yeah? I'm modulating, and you see this is not a straightforward line between the states, so we look at that in this diagram and start to understand how is it working when we are switching between the states. So that's the reality. Yeah? And here you see suddenly, okay, 90 degrees look like a lot, but you start estimating, there's a certain uncertainty already in the system, which we have to accommodate for. Yeah? So that's, I always find that very nice if you have all these smart ideas of getting the bandwidth up, and then you're sitting there and scratching your head and say, oh my God, the system is doing that to my real output. Huh? Anyway, we are continuing. Yeah? And now I'm introducing 16 QAM. Does anybody know what you are effectively losing in these? If you have some modern thing of this, what are we really using? In an iPhone, whatever it is now for you, 8 upwards. What would you guess? (16 QAM). We had 1024 by now. In anything which you would consider, if I sent you to MediaMarkt and said select the cell phone, it's either 512 or 1024. What is the problem? The problem is that we are essentially saying the system is able to provide this excessive precision. Yeah? So you say, I can discriminate here in 16 quorum, it's quite visible still. You have different amplitude states, and that is new for you, I think, you also have this distinction in phase. So you can think that an amplitude is only going by a certain margin, and then if there's noise around it, it's easy to understand in the amplitude. But you also have to get the phase correct. And if you are at 1024, then you are down to a couple of degrees of distinction between the signals. Yeah? Just to give you typical usage, 16 quorum is used for TV. So there's the TV you got by satellite, if you get it there. Now this is the terrestrial. That's the terrestrial. Is 16 quorum. So it apparently gives you some bandwidth, but there's one thing where you can see that my argument is always a bit vague. All the people have these excessive TV sets. I'm not a friend of those, but apparently people like big displays. But you have to think, if there's a big display, you also need a refresh rate to make it nice. Yeah? So you suddenly have this enormous amount of pixels which you constantly have to resupply with data. Yeah? That means that even for something as simple as a TV signal, this type of modulation is simply not efficient. It's not enough. Yeah? So even something as stupid as a display for a TV drives you, because people decide they need these 2 meters by 2 meters in the living room to have to watch certain movies or whatever. So that is what's driving us. And you can and what I'm trying to say is this excess in data rate. The reasons for that are sometimes a bit questionable, but the point is it's simply there. Yeah? So you're standing there as a system provider and start thinking, how on earth am I going to accommodate that problem? Yeah? So I asked you in the beginning, why are we driving this development of the data rate? There's many arguments, but it's getting so delicate in the distinction that we are saying the system is getting more and more linear. Yeah? And here, for example, you see that now, what I promised you earlier. This is, for example, the amplifier which is doing exactly this type of behavior. Yeah? So the big problem you have, for example, is that we suddenly have to get signals out, but we have to make sure that we are really sending them out correctly and receiving them out correctly. And on this channel, we are trying to be as linear as possible, because if we don't get that linearity in, and linearity means that we are not changing this constellation diagram, which we have carefully modulated the stuff on. Yeah? So you're very delicate, and I'm setting this point there, and then comes reality, the big channel, so to say, and big distortions. I think you said that in the beginning, all these distortions we're getting from everywhere, correct? Yeah, because you simply, all this is correct. And maybe a question, if this was an ideal diagram, how would the green areas look like? If this was perfectly ideal.
It would be very small, because we would always hit the exact point.
Yeah. And this is important, because already when we are sending away, this could be a diagram which we would already produce as the best signal source we have, and then you would put it on, you can measure this, you can really put it on a screen, and you see this thing is suddenly, and there's not a single dot, but it's an area. Yeah? And then which tells you that already the original system has some phase noise. So there's some uncertainty from the beginning, also in the amplitude, which makes the stuff already in the best way we have noisy. And then come all the transmission experiments, or what we do with them, and then hopefully something like this shows up in the end. And if not, then we have information loss. Okay. So there's one question in this room which we have to ask now, which is, why at all send only one frequency or a small fraction around that? This has to do now with the idea, if you have now modulated the stuff on for a certain bandwidth, which we are doing, then we can transport a certain amount of capacity. Question is now, we know how to, so this is for one frequency, this is what we are transporting, and now what we want to do now is, how do we do this more generally? Yeah? And the next thing I would like to ask you is, if we are now in the spectrum and we use multiple frequency, which problems do we get? Let's assume we have 10 gigahertz of carrier frequency and we make 2 gigahertz of bandwidth, which is already outrageously a lot. Yes, it's really much. So why is this already a problem? What happens to the 9 gigahertz signal and what happens to the 11 gigahertz signal in relation to the 10 gigahertz signal, which we then have, because 2 gigahertz of bandwidth around 10 gigahertz is a problem, is a nice thing. But what starts to go wrong when we are sending, for example, a 9 gigahertz signal in relation to 10 gigahertz?
I think there's a different behavior than in the atmosphere, and then there will be maybe more phase noise or something like this.
Yeah, the idea is good, but you have to be more precise. First of all, when we are sending a certain bandwidth in parallel, what do we assume? You send it away, and what do you assume on the reception side? So I'm here, I'm sending 2 gigahertz of bandwidth, I'm sending it out. And everywhere where it's detected, what has to be true to receive it in a good way? The 9 gigahertz signal has to arrive at the same time as the 10 gigahertz signal and the 11 gigahertz signal. Why could there be complications? And I think there's some easy examples where you can see that it's a problem. For example, a musical instrument, which is essentially a wave in media. Yeah? And you know that a big bass, contrabass, is bigger, which means, why is it, and it has a deeper sound, which means a longer wavelength. What is the relation between the wavelengths and the geometry that you are using in relation, for example, to a violin, which could be much smaller and produces a shorter wave or a longer frequency? What does this tell you when you send, for example, this signal which I've described before around buildings? So that you're bringing this 2 gigahertz signal to an environment. For example, you're running around the IMTEC, and the waves, they interact with, for example, buildings or rooms or even smaller things like chairs, or maybe there's a hole in here. What is the relation between wavelengths you transport?
Maybe the waves go different paths, so when we have one path that's maybe longer for one wavelength and the other one is shorter, and then we have time shift between different frequency signals.
Yeah, it's very good. So what you have to fundamentally understood, and you know this, you know that the violin produces a different sound than the contrabass. That is something you have known forever. And the problem is that if the signals they might arrive at the same time, but they're arriving at different ratios, for example, of their amplitude. So there's a different propagation, as we say, in the free air. And it's not because of the absorption, because the absorption was a particular frequency. It is, but it's not the main effect. But it is around buildings or resonating frequencies that this is the, and this is a very generic argument. Yeah? So this idea is that I can, and this has to do a lot, if you're sending now a certain spectrum with information on over a channel, then we typically assume that on this channel we only go so wide that the paths we are still comparable. Yeah? So what you cannot do is, for example, let's take the extreme, you have a 10 gigahertz signal and you use, let's say, 10 gigahertz bandwidth. So you're starting at 5 gigahertz going up to 15. Yeah? And it's clear that a 5 gigahertz signal will propagate very differently than from a 15 gigahertz signal. Yeah? So this idea is only to be taken with a grain of salt. So you can only, so what we typically like is we have a certain frequency, which we call the center or carrier frequency, and the modulation around that is only limited. Maybe, so what is the bandwidth of GSM roughly in relation to the carrier? Maybe this helps you. So GSM has 2 gigahertz of frequency, and what is the bandwidth we effectively use in kilohertz? So that's what you are using. Does anybody know? You had kilobit of bandwidth, of bit rate. So what is the assumed bandwidth that you're probably getting? It's not so wrong to say that. It's kilohertz. Yeah? So it's only very small modulation. So for this GSM, the propagation differences on the bandwidth are very minor. Yeah? For 5G, which is the latest standard, we are getting quite crazy. So we still use these 2 gigahertz, but we have already 120 megahertz bandwidth. So there's already a significance becoming available. But the trouble is that, and that is why this foil is on, there is a frequency dependence of the propagation, which is very much based to resonant behavior. And it's particularly true around buildings, and it's also particularly true when you are putting this in devices. Yeah? So that's something we, like the music instruments. Yeah. And now we are doing a concept. Yeah. So the idea of RF is quite simple. That we say, okay, we're sending a wave. And in the first place, and this is why this model which I'm now proposing to you is so useful, we are saying it is the same frequency, and we check the system for this frequency first of all. Yeah, so we say we first of all design for 2 gigahertz, and there's a little bit of change around that. Yeah, so that works pretty well. And now, following that idea, I start to design my system. Yeah? And the idea now why I'm emphasizing this so much is that in this approach, how we design those systems, we are taking a relatively strong simplification, but you can take it very far if you do it right. Yeah? And that's now the idea. And the central idea in the system thing is that we start talking about impedances. You could say, why impedances? What's this? It's boring. Maybe not, because from this we can take a very simple approach which takes us on the system level very far. So it's not just this simple idea, but we know, for example, that the impedances of a resistance is independent from the frequency. So if you have a pure resistance, there's simply no frequency dependence. Yeah? And this idea of the capacity, and you know that this impedance is 1 over I omega c, and suddenly there's omega showing up, which is the frequency. Yeah? And the same is true for the inductance, coming as a concept, which is where the impedance is proportional to the frequency. Yeah, you could say, oh my God. The idea in system theory, and that's what this, again, is the idea of this lecture, how do we build a system? Yeah? And if you take that idea, which I was just starting to explain, we are taking an approach that we say, whatever it is, whether it's a satellite, a car, something like that, or just an inductor, it has an input-output relation. Yeah, so at some frequency you send some, in this case power, to the system, and there's only two things which can happen. That's very simple. The wave can be reflected at the input, or it can go through the system. And the same is true on the other side. If I'm sending the same wave to the output of that system, I will have the same. It either goes back to the input or it's reflected. Yeah? You could say, why this? Because it deconstructs a big problem. Yeah? So, for example, it's easy when you take, for example, a simple inductor. Yeah? So it's very easy to calculate the principal idea. So the idea is, if you take that inductor now as the system, you say, I'm sending in a wave, and what I mainly will get is, of course, I will probably get something like the impedance of this system will be proportional to the frequency which I'm sending in. Yeah? And hopefully, as it's more or less symmetric, the same will happen when you look at it from the outside, from the output. Yeah? But you're already getting the problem because this system is not perfectly inductive. Why is it not perfectly inductive? You can see it here in the layout. So there's an input channel coming around, winding up, and where could also be capacity occurring? On this most simple example. So that it's not just a piece of metal which is wound up, but what could already be capacitive in this? So there's a piece of metal going underneath, turning out and forming an inductor. Where could a capacity be formed already? It's very easy to understand.
Area where the conductor is next to itself in the left point, so the outer ring has a capacity to the ring that's a little bit further.
Very good. So this is an inductor because it's only a wound up thing which you learned in physics very ideally. But you see already when you make that real, it's probably not purely inductive because these two metals also somehow have to couple capacitively. It's a very simple argument, and this is not about an inductor. We could go home. This would be too easy. The point is, even in the most simple representation, this is not going to be pure in the sense that it's simple. So this will be a mixture. So even for that, you would have to take at some point this simple effect into consideration. So what would you do? You would characterize this thing and ask, how can I build this or model this? So you would say maybe this is an inductor plus a bit of capacitance. And this guides you very far, because if you can do that for two simple ideas, you can also build a satellite with that idea. Because at the end of the day, what you are asking yourself is, a satellite is a thing which is high in the sky, which has an input signal coming in, and at some point sends it out again. And now on Earth, and if you ask yourself, what is he talking about? What I'm trying to say is, you have a system, and of course you know a satellite is built not from one component, but from 2 billion components. So, but in the end, you will only want to need what this thing does for you. And this is the right approach to talk about such systems, because we don't need to know all the possible things in voltage and current which we might take from a time domain analysis, which we could also do. The only thing we want to know when I'm sending this signal up in the sky, and what do I get back? Yeah? And for example, it can be a linear thing that if it's not built up from one component, or the satellite can be from two subsets of things, yeah? And then it can be either a linear approach in a series, or it could be an approach where I'm also going into the hierarchy. So because I know, okay, now I have distributed my satellite from 2 billion components into 2 times 1 billion components. You could say that's not really a simplification, but it's a start. Yeah? And that's how we take down systems in the frequency space, because assuming that around the frequency where we are looking at that they are behaving identically, we can start to understand them much easier from a mathematical point of view. Yeah, so what you do is you send signals into something, you know what is coming out, and this signal is then again sent into the next thing. And that helps. Yeah? And it's also consistent with this idea that we are sending in a communication signal, we are mostly sending something like one frequency plus a bit, but we are assuming for the moment that this is the same for the spectrum. So that helps us greatly. So we don't have to think about all the things which could happen in our environment. We just characterize this channel for the frequencies we are sending. Yeah? So that's the big thing which helps us in this understanding. Now I have to talk a little bit about how we look at things. And one thing which in engineering is sometimes very smart to do is to be a bit lazy and think first and then do, rather than do first and think later that it maybe was not a good idea. Yeah? And the reason why we are doing this here is the following. When we are sending something away, there's a preference to talk about power rather than voltages and currents. And there's a reason for that, which is that powers are easily measured. Yeah, so for example, if I'm sending a power into the air, what is an easy way to measure a power rather than knowing anything about its constituents, voltage and currents? How can I easily measure power? Yes. What? If I have power, for example, earlier we put power into a chicken. How can I find out how much power I put to that chicken? Or energy.
We can check how hot it is.
Yeah, we can measure temperature. Yeah? And this is a lot easier than discriminating. Okay, the chicken has a very complex surface, and it's a good example because when you're sending this field on top of the chicken, you first have to calculate all the voltages around that chicken, all the currents which are induced, integrate that, and then deduce how hot the chicken is. That is a bit complex analysis. The better way of doing that is to say, okay, the chicken I did it for so much time, chicken got hot by that temperature, so I know so much power was put into the device, or into the food in this case. And that's why and this is this general formula which I'm putting up here. So there's of course there's a clear relation between voltage and power and currents all the time. Yeah? So if I, for example, if I'm sending a wave and I know the impedance, which is the critical criterion, well, then I also can calculate the voltages and the currents. There's a direct relation which is just this. Yeah? But in many cases I'm not interested. The only thing which I would like to be knowing, I'm going over a channel, I start with 100 watts of power, I'm going through the system, I lose maybe a little bit, something is reflected, but I don't need all the details. The only thing I'm really interested in is that so much power arrives at the next point. And I don't need the details, and I can go through the system doing that. Yeah? If I had to do all this knowledge about the voltages and currents in the center, this is equivalently be done, but it's not the smartest way of doing it, because there's the relation with the impedance involved. You have to know the impedance of the chicken, but you're not really interested in that. The only thing what you want to know is starting, going to. So this is why typically we are, for the analysis when we build the systems, we sometimes go back to voltages and currents, especially with semiconductors. But in general, we just go through the channel balance. We start with a power and we arrive at a power. Yeah? So there's a preference. And now coming to that, we come into a description which is a definition where we are going away completely from the power idea, because the only thing we are effectively interested is if I'm sending a certain amount of power, percentage-wise, how much is reflected or going through. Say that again. I'm sending out a certain power, and the only thing I want to know how much is reflected at a frequency and going through and going out. Why is this a big advantage? If you're doing this with a 2 billion pieces satellite, you don't want to know all the details. The only thing you want to know, how do you go through that system? Yeah, so the only thing, if you start with some signal, and then you're multiplying yourself component-wise through the system. And there's another idea when I go back to this graph. Maybe we are cooperating. Yeah, so in a satellite, so you build the transceiver, you build the signal processing unit, you build the antenna, you build the system which produces the energy, you build the navigational thing, and all these things. So in the end of the day, we will put the satellite together in a mode of cooperation by saying, this box does this, and if I have to feed a signal in and out, that's what I get. It's aggregating maybe not a billion components, it's aggregating 100,000 components each, with the effect that I'm only interested to get the communication signals through. Yeah? It's not always going to be a completely sequential sequence, so maybe it's the navigational units put something to the bus, the communication unit put something to the bus, and so on. But you get the idea. I can deconstruct the system and I'm able to cooperate. Yeah? How many people and how many engineers have worked on this in parallel? Make an estimate. It's about 1,000. How often is this renewed? So when is, you know that? That was iPhone, whatever, 11, 12. What is the time difference? Yeah. And from this you can learn so much. There's a year difference. Going from, there's of course engineering team 1 and 2. And because it has to be a year for some reason, yeah, could also be an airplane where the sequence is maybe 7 years, but it doesn't make a difference. Here you can only see the craziness of the endeavor. 1,000 people working in parallel at iPhone 11, the next one already starting in iPhone 12. How on earth do they get something as complex as this together? You go, oh my God. Yeah? And the only thing they really do is that they take a system, rip it apart, and get everybody their assignment on the function. Yeah? And the function is this: how do you go from A1 into B2? And if something maybe is reflected, that's something we still have to talk about. There might also be something coming back. Yeah? So maybe the simplest idea is I'm sending something through a system, and at some point there's a screw a bit loose or a connector not perfect. Yeah? The system also needs to accommodate the idea that not everything is flowing perfectly without losses or without reflections. Yeah? So there's maybe some reflection going back and forth anyway, and we have to keep that down. And what we can then do is, when we are writing this up, we are just taking these power waves, and what we are, in this case, doing this as a reason for that, this is what we call the S matrix. We do, that's the following advantage. We say what is coming out of the devices at the input and the output is this matrix times the input parameters. Yeah? And input parameters in this case means, if you go back to this here, I'm probing from both sides. So this is the incoming wave, A1, and at the output, it's A2. Yeah? So this is what's flowing to the device, and I know what is coming back to me when I start that process. Yeah? The advantage is that you can essentially take that cell phone, probe it from both sides, and if it has 2 ports, and then I know the behavior of a frequency. First of all, it's not, this system, just to say it very clearly, is not typically used only with 2 ports. You can take n ports, but the idea is the same. You send signals to this thing and you get a reflection. And what is most important, of course, is that the signal which is reflected is not only coming from the input, because there's also a possibility something from the other port turns back to the input and vice versa. So just a very simple idea to make it realistic. Amplifier, you're sending something in, and you hope, of course, there's an output which hopefully is larger than what you originally put in. Yeah? The new idea is something is already reflected at the input, and that is not so difficult to understand, because not everything I'm sending to you is perfectly absorbed. There could also be a reflection. Yeah, for example, the most crazy case, if it's a short circuit, so if it's just a short circuit as an experimental thought, then everything will be reflected. Nothing is going in. Yeah. So that's the easiest case which can happen. And it can of course happen partially. So there you start to see, it makes a little bit of sense. Yeah. And when we go through the system now, that is which I would like to close. It was a lot of material today already. The idea is we're sending a wave and come to the beginning. The wave is at the carrier. You know that modulation is a little bit around that, but here we assume one frequency that comes out of this one system and is sent to the next part of the system, the one which we want to analyze. Yeah? And you're coming in with a signal and you're coming out of the system. Yeah? And now you go through a mathematical description and ask which conditions at these interfaces have to rule to make sure that the maximum energy transport occurs. And you can ask now, which situations do we have? Yeah, and the easiest one, this is always what I like, is let's assume this is the input, so this is the generator. Yeah? So this thing is not connected, so that it's not put to this next system. What would you assume if the signal comes out of this cable? What would you assume to happen? What happens here?
Just a little bit of capacitive coupling.
And if there's a wave traveling through that cable, what happens to the wave?
Reflection.
Yeah. How much? Good answer. Very good answer. Because some people think this thing could also radiate. It can, but it's typically not the case. You have to build it quite smart to make it an antenna. So this thing, as you correctly say, the signal comes in and it's totally reflected. Yeah? So a very generic thing. This has to be accommodated. So apparently this is not a condition for transmission. So now I'm connecting another cable. Assume this is the cable. And now what is defining how much energy is getting in and out? What would you say without having done the calculation? It's either totally easy, and I know you have answered the question already, and with this I would like to close. I want to give you the following task. You go to MediaMarkt and you buy a satellite transceiver. And then the person at the counter says you need a cable. Which cable? Of course you could say I take the one which fits. But maybe electrically that's a bit weak argument, although it's not so stupid. We come to that. But for reasons I never understood, you look at the back of the transceiver and it says 75 ohms, and then you go to the bar and said 50 ohms, 75 ohms, and you grab, for reasons you never thought about, 75 ohms, which is Something, you have never thought about this before, I'm sure, but you knew it has to be 75 ohms, and the answer is of course you are correct. Because what you're saying here is, the easiest thing to describe that is always to explain it. If this is a cable of 75 ohms impedance, and it's continuing with 75 ohms, there cannot be a reflection in the system. It's very simple, that you just continue, so that a cable where the wave is running will always make sure the wave is running further, unless there's an impedance change, and that is the story, which we then can also run as a calculation. You can say, now connecting the generator to the system we want to investigate, and if it's a real system, so just the impedances of a resistance, then you connect it, and so 75 ohms, and fine, you get TV. Yeah? The reason why we are doing this is very simple. There's obviously, as we talked about earlier, there's also frequency dependent and in this times imaginary impedances. So you can have, for example, a port which does not have 50 ohms or 75 ohms or 100 ohms. You can have a port, because it's a bit capacitive, which has 50 ohms minus I something. So it's a bit different impedance. Yeah? And this condition, connecting two devices, will then tell you what to do. And we get a relatively simple answer, which is what you learned before is correct. I think it's somewhere here. This is the answer. So you have to have, when you connect the two things, 75 ohms has to be 75 ohms if it's real, and if it's an imaginary impedance, the imaginary part has to just to be opposite. So if you're coming with a 50 ohms minus I 50 ohms, you have to answer with a 50 ohms plus I 50 ohms to make it match. You can say, why on earth is he telling us? The point is, you can build a satellite based on these principles. Yeah? So you can forget about some of all this voltage and whatever behavior. You can just think from the power and see what it does for you, and it's perfectly correct. Yeah? And connecting two cables, that's not what you have come for to university. That's something you could have known before, and you didn't already know before you ever thought about electronics. But there's a learning from that, because if you take that system further, we can now start to send signals over this channel and build a channel in an efficient way, and just also the opposite. Maybe I don't want, I think your interference thing from the beginning, I still like it, because for example you could say, of course I want 1 gigahertz to enter my system, but if somebody comes at 500 megahertz, what do I hope to go into the system? And the answer is no, reject. I don't want to hear from the other guys. They are killing my transceiver. Yeah? So there's also the other idea. So we can build systems over frequency which just do the channel for us and reject the rest as one idea. Yeah? Okay, it was a long lecture, but it's a bit much. Next time we're going to do a bit less, because we covered up some grounds also from the last lecture. So I hope it becomes something that starts to be reasonable. So I hope this is not just about some ideas of cell phones. It's about these systems ideas we are after. And you start to understand there's a lot more, and that's normally what I'm doing. There's also some other systems aspects, and that's, I can also do it from here, but it's not mine, so I have to be a bit careful. There's many other ideas we have in the system stuff, so especially when things go wrong. Yeah? So that's what you said. We are not, you go now to the blue sky and enjoy it. I also do, but we're also thinking about what happens if it rains, because we hope to have communication also in the rain. Thank you very much.